Okay, hello everyone. Welcome to the BIM 281 review session. I'm sorry I couldn't be with everyone today. The midterm is on Wednesday, May 4th from 1:10 to 4 o'clock p.m. Okay, and this is open book, open notes, open everything really, except it's closed internet. Okay, closed internet. So what it means is you can bring in any course material you like. You can bring in outside material as well, but you can't access the internet during the exam. So everything has to be downloaded. I have to say the problems are going to be created from scratch, so it's not going to be as helpful to fill up your mind with Fourier transform tables for Fourier transform that we didn't do in the class. Okay. And so I really think the best way to study for the exam is not to go to outside material or go to outside books, although you can certainly go for perspective. But I think the best way to study for the exam would be to do practice problems. And so you have now a wealth of practice problems, including the quizzes, the homeworks, the pre-labs, and other practice questions, as well as the practice midterm. Okay, so the idea is to really become proficient in doing these problems, and the practice is intended, should help with that. Okay, so you're not going to be asked to write essays about Fourier transforms on the midterm. You'll be asked to solve them, and so really it's really important to have a good practical knowledge or good practice with actually solving and performing these problems, doing these problems. Okay, so there are 5 problems on the exam with equal weight. They're not in order of difficulty. If you have any trouble with any given problem, move on to the next one. Put all answers in blue books provided, as well as all work. Turn in the exam with the blue book. You may use any results from the homeworks or lectures or labs without rederivation. And you may use the course webpage, but otherwise internet use is not allowed. And you have 2 hours and 50 minutes to complete the exam. So the exam is not intended to be time pressured. Inevitably, people do, some fraction of the class does take the whole time to do the exam, but I think people who may have seen some of the material before may take less time. Okay, so let's get into this. If there are any questions, send me email or ask the TA about the exam. But the design of the exam is going to be similar to the practice exams. Okay, let's get started. In this problem, problem 1, we will consider an approximation of a periodic wave using a single sinusoid. Consider the zero mean square wave shown below. Okay, that's the zero mean square wave. Then we're asked to state the Fourier series coefficients of this zero mean square wave. F of t. Okay, so what are the Fourier series coefficients? Okay, well, one way to do this would be to plug in to the analysis equation, right, using this function f of t, and integrate to determine the Fourier series coefficients that way. Now, we advocated a slightly different approach in class, and it was based on the insight that we knew already for a non-zero mean square wave, let's call it x of t, we knew the Fourier series coefficients. So we know what the Fourier series looks like for this function here. And they are that, as shown here, and actually I don't want to call these Cn, I'm going to need to pick a different number. Let's call them A. Okay. So for this non-zero mean square wave, and we had, I think this is a duty cycle here of 1/2. So this is 1 minus 1, like that. Okay, for that x of t, these were the Fourier series coefficients. Okay, so can we use that to solve the problem? Well, we showed as one of the properties of the Fourier series that actually let me do it this way. Okay, so we showed that if we can write f of t as the sum of two functions x and y, then we can write the Fourier series coefficients of f, Cn, as the sum of the Fourier series coefficients of x and the Fourier series coefficients of y. Okay, so how do we get from x of t to f of t? Well, we just subtract 1/2. That'll take us from this non-zero mean case, which we studied, or which we integrated directly, to the zero mean case here, which we're asked to solve. Okay, so now we have y of t, right? So y of t, I guess I could draw it here. So y of t is equal to minus 1/2. It's hard to draw a function that's equal to a constant, but that's what it is, right? Y of t equals minus 1/2. And we also found out that the Bn, right, which are the Fourier series coefficients of y of t, are equal to minus 1/2 if n equals 0 and 0 otherwise. Okay, and so putting all that together, and in particular putting together the an up here and the bn down here, we find that Cn, now note for n equals 0, we have an plus bn, right? So that's 1/2 minus 1/2, so that's 0. So if n equals 0, it's equal to 0. And it's equal to 1/2 sinc of n over 2 otherwise. Okay, so that's a simple way of solving this particular problem. Okay, next question. Part B. Okay, we wish to approximate the square wave using a single sinusoid with amplitude alpha is greater than 0 and phase phi. Okay, where g of t equals alpha sine 2 pi t plus phi. Okay, find the fundamental period and determine the Fourier series coefficients. Okay, so first, the fundamental period is the time it takes for the sinusoid to cycle through 2 pi phase, right? So how much does t have to increase to go through a phase shift of 2 pi? Well, that's the fundamental period, which is equal to 1. Okay, so then given that, we can set up our Fourier series analysis equation. dn equals 1 over that period, which is 1. Let's take the integral from minus 1/2 to 1/2 because we know that this function is symmetric. Alpha sine 2 pi t plus phi e to the minus, I'm sorry, excuse me. E to the minus j 2 pi n over the fundamental period, which is 1 times t dt. Okay. And now we can apply Euler's formula. E to the j 2 pi t plus phi minus e to the minus j 2 pi t plus phi over 2j times e to the minus j 2 pi nt dt. Okay. So I'm now going to divide this up into two integrals, and then we'll apply orthogonality. So now we have alpha over 2j, I'll take that out front, times the integral from minus 1/2 to 1/2. E to, now I'm going to combine these terms together. So the best way to do that is going to be, let's do it this way, e to the j 2 pi t minus n plus 1 for the first term, e to the j phi dt minus, same thing, integral e to the minus j 2 pi t, and now we have n plus 1. E to the minus j phi dt. Okay, hopefully we got that right. Then we apply orthogonality. So this term here is going to be 0 unless minus n plus 1 equals 0 unless n equals 1. and this term here is going to be 0 unless n equals -1. Okay, so another way we can write this is that dn equals alpha over 2j. Now, I forgot to say that when n equals 1, this term is equal to 1, right? Because if n equals 1, it's the integral of 1 dt from 1/2 to -1/2, right? And then we have this e to the j phi that comes out front. So we're going to have finally alpha over 2j e to the j phi if n equals 1. Same with the second term. If n equals -1, this term here, right, is going to be 1, and so we're integrating 1 from -1/2 to 1/2, which is just 1, and then this e to the minus j phi term comes out. So it's equal to minus alpha over 2j e to the minus j phi if n equals -1. Okay, I think that's right. So just to complete that thought, this is also equal to 0 otherwise. And does that make sense? Well, it does kind of make sense because a sinusoid is comprised of two complex exponentials, right? Summed together by Euler's formula. And so when we take the Fourier series of a sinusoid, we should expect that we'll only have Fourier series coefficients be non-zero for those two complex exponentials. Okay, so number C, and this one is fairly easy. So, but C, we have that Fe, or this error, is equal to f of t minus g of t. Okay, and we are told that f of t has Fourier series coefficients Cn, which we found g of t has Fourier series coefficients Bn. And so the new Fourier series coefficients, what do we call them? Oh, excuse me, these are dn's, not bn's. The new Fourier series coefficients, we know are, or we're told are En. We're not told what they are, but we're asked to find them in terms of C and D. Okay, and so we can just apply linearity here. If we subtract two functions, we also subtract the Fourier series coefficient. So En equals Cn minus Dn. Okay, and you should go back to the definition of linearity to convince yourself about why this is true. Okay. So the last question is actually a bit challenging. So it says the approximation should minimize the error, right? And so the idea was we started out with a sinusoid approximating a square wave, and we're now asked to choose alpha and phi, so the amplitude and phase of the sinusoid, to minimize the mean squared error. Right, so if you recall, this was actually the example that we did at the beginning of class. Not the beginning of class, but in the first week or so of class, where we were playing around with the MATLAB GUI, and we were trying to get an approximation for a square wave using a finite number of sinusoids. Okay, so here we're only using one sinusoid. Okay, and so you can imagine, just looking at this, right, that probably, since a sine wave is going to start down here and go up like this, that we're going to have to shift the phase in some way. So the phase is not going to be 0, because that would be a very poor approximation of the square wave. And similarly, we want to scale the amplitude of the sinusoid to best approximate the square wave. Okay, so solving this problem, we're asked to minimize the mean squared error, and we need to choose alpha and phi. Okay, so we're told as a hint that we should use Parsifal's theorem. So let's try and do that. So the sum of the error squared summed over the period, or the integral of the squared error summed over the period, which kind of tells you how different the two functions are from each other, your estimate and the target. We know that that's equal to the sum of the Fourier series coefficients squared by Parseval's theorem. Okay. And so what are the En? Well, we know that from the previous problem, those were just the difference of the Fourier series coefficients between the sinusoid and the zero mean square wave. Okay, so this is equal to and so let's actually divide this into two groups. Okay, so some of these coefficients, En, are going to depend on the amplitude and phase of the sinusoid, and others won't. Okay, so recall that En equals Cn minus Dn, right? So this was the target function, and this here was the Fourier series coefficients for the sinusoidal approximation, right? And so the error is just the sum of the differences of the Fourier series coefficients, which kind of makes sense, right? And so recall that Cn was only 0 for n equals 0, right? Or we know it's 0 for n equals 0. Actually, it's 0 for n even. Dn we know is 0 for all values of n except plus and minus 1, right? Because those are the two harmonics that contribute to the sinusoid. Okay, so let's divide it into two groups. So let's write this as the sum from n magnitude of n is not equal to 1, right? So that's n is not equal to plus or minus 1. En squared plus the sum for, well, let's not write it as a sum. Let's just write E1 squared, magnitude squared, plus E minus 1, magnitude squared. Okay. so this term here, right, and recall the Cn were in general non-zero, but Dn is only non-zero for plus and minus 1, right? So this term here is only going to be my Cn's, right? So those are not going to be affected by my estimate. Okay, so this first term is just